Welcome to this two-part mini-series, where we will be looking at the modeling of multiphysics phenomena for nozzle dynamics using Meshless methods. My name is Joubert from the University of Victoria, and in this video series we will be exploring some of the work that I've done in collaboration with Professor Wilke, also from the University of Victoria, and Professor Pizette from IMT North Europe. Before we jump right into it, I want to give a quick overview of the structure that this series will take. This video will be focused on the mathematical modeling of the multiphysics system, while the next video will look at one of our applications in detail. I will start off slowly by first motivating why exactly we care about multiphysics, and more specifically why we care about multiphase physics. While this slide does spoil the surprise a little bit by letting you know that we're interested in manufacturing, I will use the next slide to go into a little bit more detail regarding this. After that, I will introduce the idea of a Meshless Lagrangian method and explain why this is a natural choice to be used in this context. Once that is in place, we will then look at our implementation of an incompressible generalized finite difference method for solving incompressible fluid dynamics problems, as well as the multiphysics extension that allows us to implement multiphase problems, specifically by using the continuous surface force model. Once all this mathematical background is in place, we then get to appreciate what the model can do by looking at its application to a few example cases. If after all this you're still itching for a more critical discussion on this model, then I would like to direct you to the second video where we'll be looking at a detailed numerical study we carried out using this model. Specifically, we'll be looking to apply this model to a nozzle simulation to predict atomization behavior. Like I've already mentioned, our research group is currently interested in working towards process simulation of additive manufacturing technologies. This is of course an extremely overloaded term, and I think the best ways to show what this entails is to look at the fantastic results of Yu and Zhao, where they simulated powder melting in a selective laser melting process. As you can probably see, we encounter a whole range of different problems that are already challenging to solve in their independent context. This ranges from ideas like phase change, free surface evolution, to even just fluid and thermodynamic simulations. Now, it's all fine and well to say that this is a complex problem, but if we want to make progress on this, then it does help to contextualize it a little bit. For this, a useful abstraction is what I like to call the 3 M's of additive manufacturing, specifically multiphysics, multiscale, and multifidelity. So what does this mean? I think multiphysics is the easiest to understand since we can already see how it necessarily must be included from the simulation presented. All AM processes have some version of multiphysics, especially when we consider that we're always dealing with either phase change or something that closely resembles phase change when we're looking at the mesoscopic scale of the simulation. Next, we can consider multiscale. Of course, we're not really expecting the whole powder bed to undergo this very dynamic environment that we're seeing on this focus region of the simulation. And so, of course, if we're simulating the full process, it makes sense to really use very, very coarse elements when we're far away from these zones with the high dynamics. Multifidelity has a similar spirit. Of course, if we're just dealing with powders that are relatively stationary, we don't really care to model that interaction in such a high detail as, for example, the fluid dynamics inside the melting region. So what does this actually mean for the solver? Well, first of all, it means that we'll need to find a way of actually building this physics into the solver itself. This means that we'll need to come up with discretization strategies that are appropriate for things like heat transfer, fluid dynamics, of course, phase change being a big one, powder dynamics, material models, and so on. The numerical side is interesting in its own right, since here we're looking at things like data structures and techniques that are built on top of these data structures that allow us to really express ourselves when we're talking about the multi-scale behavior that we're trying to see, the adaptivity that we expect to see, things like allowing for reduced order modeling, and of course, one of the key components is that maybe it's not necessarily always a good idea to put all different solvers in one simulation environment. For example, when we're looking at something like the fluid dynamics in this case versus the powder dynamics of the bed, you might want to split those into different solvers. You'll need ways of getting that one solver's information into the other solver. And this leaves us finally with calibration. Of course, calibration in itself is probably the most important part of this pipeline to ensure that the simulation results are actually useful in understanding the physical system that you're trying to have your simulation represent. A subtle point here is that it's not necessarily the case that the correct material property when used in your simulation as a numerical parameter will give you the correct result, especially since we are dealing with these reduced order model systems and these mesoscale systems. Rather, what we're looking for is a way to build up a map that allows us to take material properties at a place that we do know that we can measure and build a way of extrapolating this information to other regions where we can then use it in a predictive context. For this, we use techniques like virtual calibration. With that context in place, I'm now going to motivate why we are looking at atomization as a way to move towards additive manufacturing simulations. So, first of all, atomization has very similar multiphysics. Of course, it's not the full-blown complexity of additive manufacturing, but it does look at one of the key aspects that we wanted to consider in isolation and build up competency in that regime, which is specifically the multiphase aspect of additive manufacturing. Of course, this multiphase aspect is probably the key physics in atomization. So if we can explore it in this context, then we do expect it to map quite well to additive manufacturing. We're also looking at atomization inside of the nozzle region, or mixing inside of the nozzle region specifically. Of course, again, not very similar types of nozzles between these two spaces, but it does allow us to ensure that the way that we're representing our boundary conditions and our geometries are expressive enough that when we get to the additive manufacturing space, again, we are confident that it can handle this. And finally, we are looking at an environment in the atomization context that has far more complex fluid dynamics than what we see in typical additive manufacturing contexts. Of course, this is a very good thing because it allows us to stress test our multiphysics model and make sure that our multi-phase implementation is very robust by the time we get to additive manufacturing. By now, I've used the term Lagrangian quite a few times, and unfortunately, that is one of those terms that also just carries a load of overweighted terms with it. So I'm just going to take a few minutes just to make sure we're clear on what I mean by Lagrangian in this context. And the way I'm going to do that is by considering the reference frames in CFD. So we have a total time derivative and a partial time derivative. And of course, the total time derivative is related to the partial time derivative by simply including the partial time derivative plus the advection term. For those of you that prefer a more graphical interpretation, when we're thinking about a Eulerian frame, we are asking about how information changes in a region of space over time, whereas with the Lagrangian picture, we're considering how information changes as the material flows through space. And so with that, we can now define a meshless Lagrangian method. Specifically, a meshless Lagrangian method is a type of computational strategy that discretizes a computational domain with a couple of continuum fields over it by a set of discrete Lagrangian points that are allowed to flow freely through space and essentially track information of a material as they flow and update. In this case, we see how it's applied to an example problem for fluid dynamics, where we've got a computational domain, the computational fields, which include your velocity fields, your pressure fields, your densities, and other fields that would build on top of that, as we'll see with the multiphysics extension, for example. And then we have the GFDE discretization, which takes the continuum field and represents it by a collection of material points that each contains their own values for velocities, pressures, and densities. And then we have our own GFD discretization that essentially allows us to build up differential operators that will then tell us how these points evolve through space and how the fields that they are associated with also evolve. When applying this in an incompressible fluid context, we end up with the incompressible generalized finite difference method. Again, like I mentioned, we have a type of differential operator that we can construct from a generalized finite difference term. Here I present an example explicitly showing how gradients are constructed for generalized finite difference methods. Of course, you can see that there are finite difference terms that are weighted by some sort of kernel function that's represented by W on this slide. And then, of course, if we have all the types of discretized gradients or discretized differential operators that we want, we can construct our general partial differential equations, of course, in the Lagrangian frame. And this really means that we just need differential operators for all of this. And for incompressible fluids, of course, we'll need gradients and Laplacian approximations. One of the more involved aspects of this method is how we go about solving the pressure Poisson equation. I'm not going to go into detail about this, but I'm just going to take a few moments to just mention what interesting aspects come out of this, since this is an implementation on the GPU. So the first thing, of course, the pressure Poisson equation does require a linear system to be solved every time step. This is how we recover pressure such that our velocity fields are divergence free. This matrix A multiplied by P is really what is really a discretized version of our Laplacian, and the B is the divergence for the unprojected velocity field. So how do we go about solving this? Well, since we're on the GPU, generally memory is more expensive than compute. So rather than going through the effort of constructing a sparse matrix A in parallel, we'd rather do fairly standard practice on the GPU and compute the multiplication of A times P, and just use that in an iterative sense to solve this equation. And the iterative solver that we're using here is a biconjugate gradient stabilized method. Up until now, we've only been discussing how to really simulate single-phase fluids. So here we can start introducing some of the more interesting aspects of it, specifically for our multiphysics extension here, we're looking at a multiphase formulation. The multiphase formulation we chosen was the continuous surface force method. The way that we build up a continuous surface force method is by assigning a type of color function to different fluid phases. This color function is then passed through a Shepherd filter, which smooths it out in regions close to an interface between different phases. By using the GFD gradient, we can then build up a surface. We can then build up the surface normal on our surface interfaces by taking the gradient of a color function for either the first phase or the second phase. We just make the choice to use the first phase. And then, of course, with this normal, we can then again use some of our GFD differential operators in order to construct a curvature, which can then be used to accelerate particles based off of some surface tension argument. Okay, and with that, we are really in a position where we can start looking at what type of behaviors we can represent. There are 3 example cases that I would like to highlight here, or 3 example classes rather, with 2 examples each. The first will be looking at instability type flows, the second will be looking at droplet dynamics, and the third case will be looking at stream mixing. So the first case that we look at is a typical instability problem with a heavy fluid on top that wants to displace the light fluid that it's sitting on top of. We can see that there is incredibly violent mixing taking place. Even for the fine particles that we're using, the mixing clearly takes place far below the scale of our minimum particle length. However, what we can see here is, of course, that the simulation remains stable, even in these cases where it really results in a type of degenerate state. And of course, this is due to our Shepherd filtering, essentially meaning that the color field results in nearly a smooth 0.5 throughout the domain, meaning that the curvature that we resolve is close to 0. To show what this looks like from the color gradient magnitude perspective, so again, this is our version of a normal vector in this case. We can see that the heavy fluid, the thin heavy fluid, is trying to again displace the lighter fluids to the side. Again, the density ratio here is quite low, ratio of 2 to 1. So we do see some significant mixing taking place. And of course, what we can see is that there is some very detailed mixing taking place with the color gradient really settling to some constant value in that center region, which of course means that essentially we can see the curvature in that area as nearly being 0. Next, we can look at this in the context of 2 multiphase objects interacting with each other. Specifically, we start with 2 bubbles that are both lighter than the fluid surrounding it. And of course, this means that they both want to rise. The smaller bubble at the bottom raises faster and mixes with the bubble at the top, causing essentially this ring structure. What you see here is a midplane slice, so what you actually end up with is a 3D structure that's a type of donut or a torus structure. Showing some similar results with a 3D view, here we have 2 droplets that are offset from each other that are colliding with each other. Here it becomes very clear that we get these torus structures that can form, and as a little bonus, we also get some smaller droplets that are now forming in the center. One thing to note here is that obviously that the thin film that forms in the center should become much thinner than the particle resolution that we're using here. And as we can see, what takes place when it gets too thin is a numerical rupture. But of course, again, fortunately, because of our smoothing that we introduce, at least the simulation still remains stable in this case. And then lastly, when we're moving closer towards the applications that we have in mind, specifically nozzle atomization, here we can see a little example case of that, where we have a heavy fluid traveling through the center cavity and 4 streams of a lighter fluid being injected into it. In this case, the velocity is relatively slow. We've got a slow-moving fluid with a high viscosity, so we're looking at low Reynolds numbers. And of course, as you can see from the outlet configuration, we get this very intricate structure that still really keeps the fluids very separate in this case. And then we can also compare it to a much higher Reynolds number case, where we can see that flow instabilities do definitely start to form in this case. We can see that there's a lot more mixing taking place. That's of course completely breaks apart that nice outlet structure that we had between the fluids, creating a much more violent mixing in our outlet condition. However, of course, like we've seen with the other cases as well, this violent mixing is not really detrimental to the stability of the algorithm. And again, we can carry out these simulations even if there are lower fidelity than what you would really require to capture the intricate flow structures that would be present in these kind of simulations. And with that, we can conclude video 1 of this series. So I hope that you enjoyed this. I hope that it was worth your time. If you have any questions or comments, please feel free to leave a comment below or to contact me at the email provided on the screen. For those of you who still want a little bit more, we did also publish 2 articles surrounding this work. The first is really a discussion surrounding the topics discussed in this video, while the second reference is more of interest for those who wish to get a bit more detail on the results from the second video. So with that, thank you so much again for watching this video, and I hope to see you in the second video.